Hey all. Today let us see what is meant by inner product of vectors. So when we calculate inner product or when we say something about inner product, so please keep it in mind that if we have two vectors inside a vector space V, suppose we have x and y over here, and if I want to represent this combination of x and y in terms of a real number, okay, so in that case we go for inner product. Okay, so it gives the inner products always gives a real number corresponding to two vectors. That is what inner product, and some more properties to be satisfied this mapping function that we can see later in this session. So when we talk about inner products, there can be two kind of inner products we can talk about. A very common inner product is dot product that you might have seen in your previous maths classes. So it is dot product is one of the, it's a special type of inner product. And also we can have general inner products. Okay, we can define another functions that satisfies this condition, like mapping two vectors to a real number. Okay, so we can see it in detail. First one, dot product. Dot product is a special case of inner product. It also gives a real number corresponding to two vectors. Okay, assume we have an xy plane like this, and this is the x vector x that has 2, 5. Okay, 2, 5 is the vector. Then y, 10, 3. Okay, those are the coordinate values for the vectors. Then how do we find the dot product? We represent it like x dot y. So that means this is the dot product. So x is the vector and y is also the vector. So we take the dot product means we write the matrix like this or the vectors like this. This is x and this is y. And this is not a normal matrix multiplication. Instead, we are multiplying the corresponding elements. So the first element of this first vector with the first element of the second vector. Okay, so 2 into 10 will be done. Then 5 into 3 will be done. So we'll get like this, and we take the sum of these two elements. Okay, 20 plus 15, and the answer will be 35. So that is the dot product of x dot y. So this will give you a scalar number. So the corresponding real number representing these two vectors, okay, that is actually 35. That is the real number. And so we are getting a real number over here or a scalar value over here. This dot product can be also called as a scalar product. Okay. And it can be written in another way like this, like x transpose y. Okay, the x dot product of x and y. X dot y is equal to x transpose y. Or we can write it like sigma I is equal to 1 to n xi ya. So that means this is the same thing we have done over here. That means we are multiplying the corresponding elements. Or we can write it in terms of matrix multiplication. Okay, so it can be rewritten like this. Okay, so other than how we can check this equation x transpose y. So x transpose, x is 2, 5. So that is the transpose will be a row vector 2, 5 into 10, 3. That is the vector y. So the correspondingly we will get it like this 20 and 15. And take the sum. This is not the matrix. It will be summed up and we will get 35. So again. Okay, so what is the advantage of this representation means it gives a representation based on the matrix multiplication. And here in the second type of equation, there is no matrix involved. We are just taking the corresponding elements and multiplying. It does not involve any matrix multiplication. Okay, so whichever is suitable for our application, we can choose. So that is a dot product. So basically, it transforms two vectors into a real number. Okay, that is happening. Then another method to calculate the dot product is like this. X dot y is equal to norm of x into norm of y into cos theta. Okay, this is another method to find out the dot product. And what is theta? Suppose x and y are these vectors, and theta is the angle between them. So how do we calculate this norm of x? Norm of x will be the we can calculate it using L1 norm or L2 norm or whatever. Okay, and correspondingly y also. Then the definition for the inner product, the first definition is like this. Let V be a vector space and OM, the mapping OM from V cross V to R, be a bilinear mapping that takes two vectors and maps them onto a real number. Okay. Then OM is called symmetric if OM xy is equal to OM yx for all xy belongs to V. That is, the order of the argument does not matter. Okay, so that means whenever we define a function that maps V cross V to R, okay, that means it takes two vectors as arguments and it returns a real number. And in that case, when we define a function like that, and we want to make it as the inner product, then that function should be symmetric. Symmetric in the sense, the order of the arguments should not be should not be mattered, because if it should be equal, that means OM of xy should be equal to OM of yx. Okay, it should these two things should give the same answer. So that kind of functions are called symmetric functions. Okay, so when we choose a function as inner product, that should be symmetric. That is the first condition. Then OM is called the positive definite if for all x belongs to V bar 0, set 0, that means that we take the set V which excludes 0. Okay, we exclude 0 vector and take the remaining vectors, all non-zero vectors. Okay, x is all non-zero vectors, such that OM of xx should be greater than 0. And if OM of 0, 0 is equal to 0. Okay, that means that when OM of x is equal to 0, then x should be a 0 vector. Okay, so that is the case that when we find this mapping, when we find the mapping from V cross V to R, it should always give a positive value. And when it gives 0, when both the vectors are 0 vectors, then only it gives the 0 value. So that is the second condition to make a function as inner product. Okay, positive definite. So we should understand these two. We should remember these two things. First of all, inner product is we are taking two vectors from the same vector space and map it to a real number. Okay, and we can choose any function that maps two vectors to a real number. And when we choose those functions, that should be symmetric. That should be symmetric as well as positive definite. Then only we can call it as an inner product. Then the second definition is goes like this. Let V be a vector space and omega from V cross V to R be a bilinear mapping that takes two vectors and maps them onto a real number. Then a positive definite symmetric bilinear mapping from V cross V to R is called an inner product on V, represented as like this. So this is the representation we use. Within angle brackets we give the parameters. Okay, the pair V and the inner product is called an inner product space or real vector space with the inner product. Okay, so the set of vector space and the operation is the inner product. Okay, we can call the group V inner product as an Euclidean vector space. Okay, so these kind of vector spaces are called Euclidean vector space. So that is the second definition says that if we have a mapping like this, OM from V cross V to R be a bilinear mapping that takes the vectors that takes two vectors and maps them to a real number. So then if it should be inner product, if this function, if this mapping to be a real number, then this mapping should be positive, definite and symmetric. That is the main condition. And this group will be called the Euclidean vector space. Okay. For example, we can consider V is equal to R2. So take the 2D space as the vector space. Then consider a sample inner product as follows. Like this inner product, like we take this function, this as an inner product function. Okay. This is a different inner product. Okay. Even we can say x dot y is an inner product. Okay, x dot y is will also give us a real number. So I can consider this as an inner product because x dot y and y dot x both are same, and it will give you positive value. Positive value, that is positive definite. So dot product is an inner product. Similarly, you can choose another any other function as an inner product. So in this example, we have taken this function x1 y1 minus x1 y2 plus x2 y1 plus 2x2 y2. So this can be taken as an inner product. Okay. So it is different from dot product. Okay. So similarly, we can take any function that satisfies the symmetry and positive definiteness for as the inner product. Then symmetric positive definite matrix. So we have to choose a matrix like this in order to define an inner product function, or that mapping function can be represented in terms of a matrix. So that matrix should be symmetric positive definite. So let's check this condition. For all x belongs to V bar set 0, that means all the non-zero vectors. X means all the non-zero vectors such that x transpose Ax is greater than 0. Okay, so here we are defining a new inner product function like this, x transpose Ax. And what is A? A is a symmetric positive definite matrix. Okay, and its value should be greater than 0 or greater than or equal to 0. So two conditions can be there. A symmetric matrix A belongs to Rn by n that satisfies the above relation is called a symmetric positive definite. Okay, so when we choose a matrix, symmetric matrix A that satisfies this condition, that matrix will be called a symmetric positive definite matrix. And if it satisfies greater than or equal to, okay, if only greater than or equal to holds in the above relation, then A is called a symmetric positive semi-definite matrix. Okay, it is semi-definite. If it is, it satisfies this equality also, then it is called positive semi-definite. Okay, and why do we go for this method? Means using this expression, I can represent another inner product. Okay, other than dot product. Okay. Then we can take an example. So two symmetric positive definite matrices have been taken. A1 is equal to 9665. A2 is equal to 9663. And assume x is equal to x1, x2. Okay, that is the matrix we have. Check whether A1 and A2 are symmetric and positive definite. So symmetry we can directly check. Okay, this that means A1 should be equal to A1 transpose. Then it is symmetric. Okay, so when we take the symmetry, this A1 is a symmetric matrix. Okay, so and if you consider A2, that also symmetric. And now we have to check whether it is positive definite. And to check that, we have to check this equation. That is x transpose A1 into x. Find out. Okay, x transpose x is this one, x1, x2. So find this one. Then into, it is purely matrix multiplication, 9665 into x1, x2. So we will get the equation like this, 9x1. 9x1 square plus 12x1 x2 plus 5x2 square is equal to, then we simplify it, we will get it like this, 3x1 plus 2x2 the whole square minus x2 the whole square. It will be always greater than 0. we can check it with different values for x. Then we'll always get greater than 0. So we can say that A1 is symmetric and positive definite matrix. And A1 is symmetric and positive definite. And let's check what is A2. What happens to A2? So similarly, instead of A1, we have to put A2 and find out. Okay. So it is 9663. That is symmetric. Okay, it is a symmetric matrix. Now we have to check the positive definite nature. So we'll find out A transpose A to X. Okay, equal to X1, X2, 9663, X1, X2. Okay, so we multiply it and we get any statement, polynomial like this, 9x1 square plus something like that. Okay. And this can be, this value, this can be 0 when we take x is equal to 2 minus 3. For example, for some values of x, this may become 0. Okay, it may be equal to 0 for some values of x. So we take this value 2 minus 3. So in that case, it is minus 9. That means that it is less than 0. So greater than or equal to also, it is also not satisfied here. So we are getting a negative value over here. So what does it mean? But that means that A2 is not a positive definite matrix. A2 is not positive definite. A2 is symmetric. A2 is a symmetric matrix, but it is not positive definite. And next, if A belongs to Rn by n is a symmetric positive definite, then inner product can be defined like this. Inner product of xy is equal to x transpose ay. Okay, so this is another inner product function. It defines an inner product with respect to an ordered basis B, where x cap and y cap are the coordinate representation of xy belongs to V with respect to the basis B. Okay, so here we are defining another inner product other than dot product. Okay, so similarly we can have another any other function to represent the inner product. Okay, so this is one of the methods. And in this, what is the condition? A should be this matrix. A should be a symmetric positive definite matrix. Okay, that is the condition over here. And the theorem goes like this. For a real valued finite dimensional vector space V and an ordered basis B of V, it holds that the inner product such that V cross V to R is an inner product if and only if there exists a symmetric positive definite matrix A belongs to Rn by n with inner product is equal to x transpose A y. Okay. So the inner product definition is like this. Okay. So we can say that this there is an inner product like this only if there is a matrix, symmetric positive definite matrix A exists here. Then only we can find an inner product for this. Then the properties of the inner products are like this. The following properties holds if A belongs to Rn by n is symmetric and positive definite. The null space or kernel of A consists of only of 0 because x transpose Ax is greater than 0 for all x not equal to 0. This implies that Ax not equal to 0 if x not equal to 0. Okay, so in this mapping, what happens is the kernel of the vector space will contain, suppose what was kernel, we have V and we have W. And when we map some vectors to the normal neutral element in the vector space W. So this is the kernel. So which are the vectors over here are mapping to the neutral element of W or zero vector of W. So those set of vectors are called the kernel. Okay. So what this first property says that the kernel of A will consist only of 0. Okay, so this kernel will contain only 0 vector of vector space V. Okay, that is the condition because it is a positive definite matrix. Okay, that is why it should be always greater than 0. Then the second condition is the diagonal elements aii of A are positive. Okay, all the diagonal elements, when you take all the diagonal elements, that should be positive in order to make that the multiplication with the or the inner product of the base vectors should be greater than 0. Okay, so all the diagonal elements should be positive. Okay, then only the transformation of basis vectors should be positive. So that is all about the inner products. So keep it in mind that inner products are used to map two vectors into a real number. That is the basic purpose of inner products. Okay. So based on the inner product function we are using, this real number may vary. Okay, for the same xy value, we may get different real numbers for different inner product functions. For dot product or for x transpose ax, for all these we will get different real numbers. But basically, inner product always represents a real number corresponding to two vectors. That is all about inner products. Thank you.